Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. How aliens could breathe different atmospheres. When we imagine aliens visiting Earth in science fiction, they often step out of their spacecraft and breathe our air without difficulty, or they wear helmets and breathing apparatus because our atmosphere is toxic to them. Both scenarios recognize a fundamental truth. The atmosphere that sustains one form of life might be useless or deadly to another. On Earth, oxygen is essential for most complex life, powering the high-energy metabolisms of animals through cellular respiration. But oxygen wasn't always abundant in Earth's atmosphere, and even today, many organisms live without it, thriving in environments where oxygen is scarce or absent. Understanding how aliens could breathe different atmospheres means understanding the relationship between atmospheric gases and metabolism, the chemistry of energy extraction, and the remarkable adaptability that evolution can produce when organisms face different atmospheric conditions. Earth's atmosphere is about 78% nitrogen and 21% oxygen, with trace amounts of argon, carbon dioxide, water vapor, and other gases. This composition seems normal because it's all we've known, but it's actually quite unusual from a cosmic perspective. Oxygen is highly reactive. It combines readily with many elements, forming oxides that are stable and chemically inert. Free oxygen shouldn't persist in a planet's atmosphere for long unless something continually replenishes it. On Earth, that something is photosynthetic life. Plants, algae, and photosynthetic bacteria capture sunlight and use its energy to split water molecules, releasing oxygen as a byproduct. Without life constantly producing oxygen, Earth's atmosphere would gradually lose its oxygen as the gas reacted with rocks, metals, and organic molecules, eventually leaving an atmosphere dominated by nitrogen and carbon dioxide. For the first 2 billion years, or more of Earth's history, the atmosphere contained very little free oxygen. Early life evolved in this oxygen-poor world, using different metabolic pathways that didn't require oxygen. Even today, many organisms live in oxygen-free environments, deep in ocean sediments, in the intestines of animals, in waterlogged soils, where oxygen cannot penetrate. These anaerobic organisms use alternative molecules as the final electron acceptors in their metabolism. Some use sulfur compounds, reducing sulfate to hydrogen sulfide, the gas that smells like rotten eggs. Others use nitrates, producing nitrogen gas. Still others use carbon dioxide itself, producing methane. These metabolisms are less efficient than oxygen-based metabolism, releasing less energy per molecule of food consumed, but they work well enough to sustain life. An alien planet that never developed photosynthetic life might retain an oxygen-poor atmosphere indefinitely. Life on such a world would necessarily use anaerobic metabolism, breathing gases we would consider unusual or toxic. Hydrogen sulfide, lethal to most Earth animals, could serve as the oxidizing agent in alien metabolism. Organisms might inhale hydrogen sulfide and exhale elemental sulfur or some other sulfur compound. Their biochemistry would be built around sulfur chemistry, the way ours is built around oxygen chemistry. These aliens would find Earth's oxygen-rich atmosphere as toxic as we find hydrogen sulfide. Oxygen would react with their sulfur-based biochemistry, disrupting the carefully balanced chemical reactions that keep them alive. Methane represents another possibility. Methane is a simple molecule, one carbon atom bonded to 4 hydrogen atoms, and it exists as a gas at temperatures where water is liquid. Some Earth organisms produce methane as a waste product of their metabolism, and these methane-producing microbes, called methanogens, thrive in oxygen-free environments, like swamps, rice paddies, and the digestive systems of cattle. Methane is flammable in the presence of oxygen, but in an oxygen-free atmosphere, it's stable. A planet with abundant methane in its atmosphere might support life that uses methane in its metabolism, perhaps breaking down methane to extract energy or using methane as a raw material to build more complex organic molecules. Titan, Saturn's largest moon, has an atmosphere dense with nitrogen and methane, with no free oxygen. The surface temperature hovers around -180 degrees Celsius, cold enough that water is frozen as hard as rock, while methane exists as liquid in lakes and seas. If life exists on Titan, a big if, but not impossible, it would necessarily be adapted to breathe this nitrogen-methane atmosphere and might even metabolize in ways that involve liquid methane rather than liquid water. Such organisms would be completely incompatible with Earth's environment. Bringing them to Earth would be like throwing a fish into a furnace. The heat alone would destroy them before oxygen toxicity became an issue. Carbon dioxide-rich atmospheres present another scenario. Venus has an atmosphere that's about 96% carbon dioxide, creating a crushing surface pressure about 90 times Earth's atmospheric pressure, and a runaway greenhouse effect that raises surface temperatures to over 450 degrees Celsius. No life could exist in Venus's current conditions, but a cooler planet with a carbon dioxide atmosphere and might be habitable. Some Earth organisms already tolerate high carbon dioxide levels that would kill humans. Deep-sea hydrothermal vent communities, for instance, experience high carbon dioxide concentrations dissolved in water. Organisms adapted to such environments have specialized biochemistry that allows them to function despite the high carbon dioxide. Aliens from a carbon dioxide-rich world might metabolize in ways that involve carbon dioxide directly. Perhaps they would use carbon dioxide as an oxidizing agent, combining it with hydrogen-rich compounds to extract energy, producing methane or other hydrocarbons as waste products. Or they might use carbon dioxide as a raw material, building organic molecules from carbon dioxide the way plants do, but doing so as part of their metabolic processes rather than as a separate photosynthetic function. These aliens might find oxygen toxic and carbon dioxide essential, the opposite of most Earth animals. Ammonia is another gas that could potentially play a role in alien respiration. Ammonia is toxic to most Earth life, disrupting pH balance and interfering with normal biochemistry. But at lower temperatures, ammonia can exist as a liquid, and some scientists have speculated that ammonia could serve as a solvent for biochemistry on very cold worlds, potentially replacing water. An atmosphere with significant ammonia might support organisms that breathe ammonia, using it in their metabolism in ways we can barely imagine. The chemistry would be entirely different from oxygen-based metabolism, operating through different pathways and producing different waste products. Chlorine and fluorine, both highly reactive halogens, represent more exotic possibilities. These gases are extremely reactive and toxic to Earth life, but that's precisely because they're good at accepting electrons, the same property that makes oxygen useful for metabolism. An organism that evolved in an atmosphere containing chlorine or fluorine might use these gases the way we use oxygen, combining them with food molecules to extract energy. The waste products would be chlorides or fluorides rather than the water and carbon dioxide that Earth animals produce. Such organisms would find Earth's atmosphere lacking. Our oxygen, while reactive, wouldn't fit into their chlorine-based or fluorine-based biochemistry. They would suffocate in our air despite it containing a highly reactive gas. The partial pressure of gases matters as much as their chemical identity. Partial pressure is the pressure contributed by a specific gas in a mixture. For instance, Earth's atmosphere has a total pressure at sea level of about 1 atmosphere and oxygen makes up 21% of that, so oxygen's partial pressure is about 0.21 atmospheres. Humans need oxygen at roughly this partial pressure to survive. Too little at high altitudes where atmospheric pressure drops and we suffer hypoxia, unable to get enough oxygen into our blood. Too much in pure oxygen at high pressure, and oxygen becomes toxic, causing seizures and lung damage. Aliens would have similar constraints based on their biochemistry. An alien that breathes hydrogen sulfide might need it at a specific partial pressure. Too little, and their metabolism cannot function efficiently. Too much, and it becomes toxic even to them. This means that even if two species breathe the same gas, they might not be able to share the same atmosphere if they require different partial pressures. An alien adapted to breathe oxygen at very low partial pressures, perhaps from a high-altitude environment or a planet with thin atmosphere, might suffocate in Earth's oxygen-rich air, not from lack of oxygen, but from oxygen toxicity. Temperature affects which molecules can exist as gases. On Earth, at our range of temperatures, nitrogen, oxygen, carbon dioxide, and water vapor exist as gases, while water also exists as liquid. On a much hotter planet, perhaps one close to its star, gases we don't encounter might be common. Sulfur compounds that are liquids or solids on Earth might be gases on a hot world. Metals like mercury or even iron could exist as vapor in the atmosphere of an extremely hot planet. Life on such a world, if it could exist at all, might breathe exotic gases that would condense into liquids or solids in Earth's relatively cool atmosphere. Conversely, on extremely cold worlds, gases that are common on Earth might be frozen solid. On Pluto, where temperatures drop to around -230 degrees Celsius, nitrogen, which makes up most of Earth's atmosphere, freezes into solid nitrogen ice. Pluto's thin atmosphere consists of nitrogen, methane, and carbon monoxide that sublimates from surface ices when Pluto is closest to the Sun in its elliptical orbit, then freeze back out when Pluto moves farther away. Life on such a cold world would need to breathe gases that remain gaseous at these extreme temperatures, or it would need to exist in warmer subsurface environments where different conditions prevail. The evolution of breathing mechanisms would differ based on atmospheric composition and pressure. On Earth, animals evolved lungs, gills, tracheal systems, and other specialized structures to extract oxygen from air or water. Fish gills expose blood to water flowing past thin membranes, allowing oxygen to diffuse from water into blood. Insect tracheal systems deliver air directly to cells through branching tubes. Mammalian lungs use millions of tiny air sacs to maximize surface area for gas exchange. Each system is optimized for extracting oxygen from Earth's atmosphere or water. Aliens breathing different atmospheres would evolve different respiratory structures optimized for their specific gases. An alien breathing a very dense atmosphere, perhaps with pressures many times Earth's, might have very small respiratory surfaces because gases would diffuse quickly at high pressure. An alien breathing a thin atmosphere might need enormous respiratory organs to capture enough of their necessary gas. An alien breathing a gas that dissolves poorly in their body, fluids might need respiratory pigments, molecules like hemoglobin in our blood, specifically designed to bind and transport their particular gas. Some aliens might not breathe at all in the sense of moving gases in and out of their bodies. Single-celled organisms on Earth absorb oxygen directly through their cell membranes without any respiratory system. An alien with a radically different body plan, perhaps resembling Earth's sponges or fungi more than animals, might absorb needed gases through its entire surface area, rather than through specialized breathing organs. Or an alien might rely entirely on anaerobic metabolism happening within its cells, never needing to extract gases from the environment at all, living on chemical energy stored in molecules absorbed from its surroundings. The possibility of breathing different atmospheres means that habitable zones around stars become more complex. The traditional habitable zone focuses on temperature, the range where liquid water can exist. But a habitability zone could be defined for any solvent and any metabolic gas. There's a methane habitability zone at different temperatures where methane is liquid. There's a hydrogen sulfide habitability zone where that gas exists at suitable pressures. There's an ammonia habitability zone at very cold temperatures. Each zone would support fundamentally different kinds of life, adapted to its specific conditions. If humans ever encounter aliens, the atmospheric incompatibility would be one of the first obvious differences. We couldn't share environments without life support equipment. An alien from an ammonia world would need refrigeration and ammonia supplies to survive in Earth's environment. We would need oxygen supplies and temperature regulation to survive in theirs. Even communication would be affected. Sound travels differently in different atmospheric gases. In a dense carbon dioxide atmosphere, sound would be lower pitched and quieter. In a thin hydrogen atmosphere, sound would be higher pitched and travel faster. An alien's voice might be physically impossible for human ears to hear without electronic translation. How aliens could breathe different atmospheres ultimately reflects the diversity of chemistry and the flexibility of evolution. Life adapts to available conditions, and the chemistry that powers metabolism is not limited to oxygen and carbon dioxide. From hydrogen sulfide to methane, from ammonia to chlorine, from thin atmospheres to crushing pressures, from scorching heat to numbing cold, life, if it exists elsewhere, would develop respiratory systems suited to its world's specific conditions, breathing atmospheres that might kill us in seconds, while finding our oxygen-rich air as toxic and alien as we would find theirs, proving that the breath of life can take as many forms as there are worlds scattered across the universe. How extraterrestrial plants could photosynthesize. Photosynthesis, the process by which plants, algae, and certain bacteria capture light energy and convert it into chemical energy, powers most of Earth's ecosystems. Green plants absorb sunlight, split water molecules, combine carbon dioxide from the air with hydrogen from the water, and produce sugars while releasing oxygen as a byproduct. This process transformed Earth's atmosphere from oxygen-poor to oxygen-rich over billions of years, enabling the evolution of complex animal life. Photosynthesis seems so central to life that we naturally wonder whether alien plants on distant worlds would photosynthesize in similar ways. The answer is nuanced. While capturing energy from starlight would likely be advantageous for life on any illuminated world, the specific chemistry and mechanisms of alien photosynthesis would differ dramatically depending on the star's properties, atmospheric composition, available pigments, and evolutionary history of each world. On Earth, photosynthesis centers on chlorophyll, a complex molecule containing magnesium at its center, surrounded by a ring structure that absorbs light strongly in the red and blue portions of the spectrum, while reflecting green light, which is why plants appear green. Chlorophyll's absorption spectrum is not random but reflects the properties of sunlight. Our Sun is a yellow dwarf star with a surface temperature around 6,000 degrees Celsius, emitting light most strongly in the visible portion of the spectrum that our eyes evolved to see, with peak emission in the green-yellow range. Plants evolved pigments that absorb the abundant wavelengths while reflecting the less useful portions. But most stars in the galaxy are red dwarfs, cooler, smaller stars with surface temperatures around 3,000 degrees that emit most of their light in the red and infrared portions of the spectrum. A planet orbiting in the habitable zone of a red dwarf would receive much less visible light and far more infrared radiation than Earth receives from our Sun. Photosynthetic organisms on such a world would need to adapt to this shifted spectrum, likely evolving pigments that absorb infrared light rather than visible light. Capturing infrared photons presents challenges because each infrared photon carries less energy than a visible light photon. On Earth, Chlorophyll uses two photons, absorbed at different stages of photosynthesis, to extract enough energy to split water molecules, which requires significant energy input. With lower energy infrared photons, alien photosynthesis might need to capture 3 or even 4 photons per reaction to gather sufficient energy, making the process less efficient. However, red dwarf stars are extremely common and extremely long-lived, shining for trillions of years compared to the Sun's 10 billion year lifespan. So even if photosynthesis is less efficient under red dwarf light, organisms would have enormous amounts of time to evolve and adapt. The pigments that absorb infrared light would likely appear black or very dark to human eyes because they would absorb nearly all visible light in addition to infrared. A forest on a red dwarf planet might be covered in black vegetation, maximizing absorption of every available photon from the dim red star. This is the opposite of Earth's green plants, which reject green light as insufficiently useful. On a planet where photons are precious, wasting any light would be disadvantageous, so evolution would favor organisms that capture everything. Conversely, planets orbiting hot, bright blue or white stars would receive intense ultraviolet radiation, along with visible and infrared light. Ultraviolet photons carry high energy, potentially too much energy, as UV light damages DNA and proteins. Photosynthetic organisms on such worlds might evolve pigments that specifically avoid ultraviolet absorption, reflecting or dissipating UV light while capturing only visible wavelengths. Or they might evolve protective mechanisms, UV-absorbing compounds in outer cell layers, extremely efficient DNA repair systems, or pigments that can safely handle high-energy photons by converting excess energy into heat or fluorescence. The color of alien plants would thus depend on their star's spectrum. Under orange K-type stars, plants might be red or orange, reflecting the most common light while absorbing other wavelengths. Under blue stars, plants might be yellow or orange. The specific colors would depend not just on what light is available, but also on what pigments evolution happens to discover and what combination of wavelengths provides optimal energy capture. Multiple pigments working together might be advantageous. On Earth, plants contain several pigments beyond chlorophyll, carotenoids, that absorb blue and green light, appearing yellow, orange, or red, and other accessory pigments that expand the range of useful wavelengths. These accessory pigments capture light that chlorophyll misses and transfer the energy to chlorophyll for use in photosynthesis. Alien plants might evolve even more diverse pigment systems, with perhaps 5 or 10 different pigments, each specialized for different wavelength ranges, collectively capturing a broader spectrum than Earth's photosynthetic organisms manage. The electron transport chains that actually convert light energy into chemical energy might use different chemistry than Earth's photosynthesis. On Earth, photosynthesis splits water molecules to extract electrons, releasing oxygen gas as waste. But water splitting is energetically demanding. It requires significant light energy input. An alien photosynthesis might use different electron donors that are easier to oxidize than water. Hydrogen sulfide, for instance, is easier to split than water and was likely used by early photosynthetic bacteria on Earth before oxygen-producing photosynthesis evolved. A planet with abundant hydrogen sulfide might develop photosynthetic life that remains at this stage indefinitely, producing elemental sulfur rather than oxygen as waste. Iron compounds, organic molecules, or even molecular hydrogen could serve as electron donors in alternative photosynthetic pathways. Each would produce different waste products. Iron photosynthesis might precipitate iron oxides. Organic-based photosynthesis might produce various carbon compounds, and hydrogen-based photosynthesis might produce protons that combine with other elements. None of these would generate an oxygen-rich atmosphere, demonstrating that photosynthesis doesn't necessarily equal oxygen production. The carbon source might also vary. Earth plants use carbon dioxide from the atmosphere as their carbon source, but CO2 concentrations vary dramatically across different worlds. Venus has a thick CO2 atmosphere, but is far too hot for life as we know it. Mars has thin atmosphere that's mostly CO2, but overall, CO2 availability is low due to the low pressure. A planet with very low atmospheric CO2 might require photosynthetic organisms that can concentrate and capture CO2 extremely efficiently, perhaps with specialized structures or enzymes far more effective than Earth's plants possess. Alternatively, alien photosynthesis might use carbon sources other than CO2. Carbon monoxide, methane, or even dissolved bicarbonate in water could provide carbon for building organic molecules. Each source would require different enzymatic machinery and would produce different end products. Methane-based photosynthesis might produce more complex hydrocarbons, essentially reversing the process that creates methane on Earth. ICO-based photosynthesis might build organic molecules through different chemical pathways than CO2-based photosynthesis uses. The physical structure of alien photosynthetic organisms might differ radically from Earth's plants. Trees evolved on land where structural support is needed to compete for sunlight, growing tall to shade competitors. But on a planet with perpetual dense cloud cover, blocking direct sunlight and providing only diffuse illumination, there would be no advantage to height. All locations would receive similar light levels. Plants might remain low-growing, perhaps forming dense mats rather than tall structures. On a planet with a very thin atmosphere, providing minimal structural support, perhaps Mars if it ever hosts photosynthetic life, organisms might need to be extremely sturdy and low-profile to withstand wind without atmospheric cushioning. Or on a high-gravity world, the structural challenges of growing tall might be prohibitive, keeping photosynthetic organisms close to the ground in spreading horizontal forms rather than vertical trees. Aquatic photosynthesis might dominate on ocean worlds. Earth's oceans contain vast amounts of photosynthetic organisms, phytoplankton, algae, and photosynthetic bacteria that drift or swim in the water column, capturing sunlight in the upper illuminated layers. On a world covered entirely by ocean, with no dry land, all photosynthesis would necessarily be aquatic. These organisms might evolve greater efficiency at capturing dim light filtered through water, or might develop gas-filled structures to regulate their depth, staying in the optimal light zone. Deep-sea photosynthesis might even be possible using not sunlight, but the faint light produced by hydrothermal vents or bioluminescence. On Earth, some photosynthetic bacteria near deep-sea vents use the faint thermal radiation from the hot vent fluids. This produces very little energy, but it demonstrates that photosynthesis isn't absolutely dependent on sunlight. An alien world with extensive hydrothermal activity might develop photosynthetic life that uses volcanic light, living in eternal darkness sustained by geothermal rather than solar energy. Bioluminescence-powered photosynthesis could create bizarre ecological cycles where organisms generate light through chemical reactions, other organisms use that light for photosynthesis, and the products of photosynthesis support the light-generating organisms. This would be less efficient than using a star's light directly. But on a rogue planet drifting through interstellar space with no star, such a system might be the only way photosynthesis could exist at all. The efficiency of photosynthesis varies greatly on Earth, with most plants converting only 1 to 2% of incoming light energy into chemical energy stored in sugars. This low efficiency reflects various constraints and trade-offs in the photosynthetic machinery. Alien photosynthesis might achieve higher efficiency through different molecular mechanisms, different pigment arrangements, or different metabolic pathways. Alternatively, on worlds where light is extremely dim, even 1 or 2% efficiency might be insufficient, driving evolution toward photosynthetic systems that capture and convert light more effectively, perhaps achieving 5 or 10% efficiency through molecular innovations not present on Earth. Timescales of photosynthesis might differ on other worlds. Earth's photosynthesis operates on timescales of milliseconds to seconds for individual reactions, constrained by the speed of enzyme reactions at Earth's temperatures. On a very cold world, reaction rates would be much slower. Photosynthesis might take minutes or hours for reactions that complete in seconds on Earth. This would mean slower growth rates and organisms that live life in slow motion from our perspective. On a hot world, reactions might proceed faster, allowing rapid photosynthesis and potentially faster growth, though this would also require dealing with the instability of biological molecules at high temperatures. The evolution of photosynthesis on Earth took hundreds of millions of years, with simpler forms appearing first and the complex, oxygen-producing photosynthesis we see in plants evolving later. On alien worlds, the evolutionary trajectory might differ. Perhaps photosynthesis evolves quickly, becoming established within the first billion years of life's appearance. Or perhaps it never evolves at all, with life remaining dependent on chemical energy from geological processes rather than light energy. Photosynthesis, while extremely useful, is not inevitable. It requires specific evolutionary innovations, including light-sensitive pigments, electron transport machinery, and carbon-fixing enzymes. A planet might have abundant life that never discovers photosynthesis, remaining microbial and chemosynthetic indefinitely. The seasonal variations on alien worlds would influence photosynthetic strategies. A planet with extreme axial tilt might experience dramatic seasonal variations in light availability, requiring photosynthetic organisms to either hibernate during dark seasons, store energy during bright seasons, or maintain alternative metabolic modes that don't require light. A tidally locked planet with one side permanently facing its star would have a permanent light side and permanent dark side, with photosynthesis possible only on the lit hemisphere or in the twilight zone between light and dark. The atmospheric chemistry would affect what wavelengths reach the surface. Earth's ozone layer absorbs harmful ultraviolet light, preventing it from reaching the surface. A planet without an ozone layer would expose surface organisms to intense UV, requiring either UV protective mechanisms or restriction of photosynthetic life to water, which naturally blocks UV. A planet with a different atmospheric composition, perhaps with sulfur compounds, nitrogen oxides, or exotic hazes, would filter light differently, creating different wavelengths available at the surface, and thus different optimal pigments for photosynthesis. How extraterrestrial plants could photosynthesize encompasses a vast range of possibilities shaped by stellar spectra, atmospheric filtering, available chemistry, and evolutionary contingency. From black plants absorbing every photon under dim red suns to colourful organisms reflecting abundant high-energy light under bright blue stars. From water-splitting oxygen producers to hydrogen sulfide users releasing sulfur. From rapid tropical growth to slow cold world metabolism, alien photosynthesis would adapt to each world's unique conditions while performing the same basic function, capturing light energy and converting it into chemical energy that powers ecosystems, potentially creating oxygen-rich atmospheres, modifying planetary chemistry in detectable ways, and revealing through their presence that life has discovered on distant worlds what it discovered on Earth. That starlight, properly harnessed through molecular machinery, shaped by billions of years of evolution, can power the chemical reactions that sustain living things, turning distant stars into energy sources for biology across the galaxy. How life could exist on other planets. For billions of years, Earth has been teeming with life, from microscopic bacteria in the deepest ocean trenches to massive blue whales swimming through the seas, from fungi spreading through forest soil to humans building cities and reaching for the stars. But Earth is just one planet orbiting one star in a galaxy containing hundreds of billions of stars, in a universe containing hundreds of billions of galaxies. The question that haunts astronomers, biologists, and anyone who has ever looked up at the night sky is simple yet profound. Could life exist somewhere else? And if it does, what would it need to survive? The search for life beyond Earth begins with understanding what life actually requires. On Earth, all known life shares certain fundamental characteristics. Life requires liquid water as a solvent, a medium in which chemical reactions can occur. It needs a source of energy, whether from sunlight through photosynthesis or from chemical reactions in deep-sea hydrothermal vents. It requires raw materials, elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur that form the building blocks of proteins, DNA, and cell membranes. And it needs time, stable conditions lasting long enough for life to emerge from non-living chemistry and evolve into complex forms. Water stands out as the most critical requirement for life as we know it. Water is an exceptional solvent, capable of dissolving more substances than almost any other liquid. Its unique properties, remaining liquid across a wide temperature range, expanding when it freezes, having strong surface tension, make it ideal for biochemistry. Water molecules interact with each other and with other molecules in ways that facilitate the complex chemistry life requires. Every known organism on Earth, from the simplest bacterium to the most complex animal, depends on liquid water. This dependence on water defines what astronomers call the habitable zone around every star, the range of distances where a planet's surface temperature allows water to remain liquid. For our Sun, this zone extends roughly from just inside Earth's orbit to just beyond Mars. Venus orbits too close. Despite having had water in its distant past, the intense solar heating drove a runaway greenhouse effect that boiled away the oceans and left a hellish world with surface temperatures hot enough to melt lead. Mars orbits near the outer edge, cold enough that most water exists as ice, though liquid water might occasionally form in certain locations under special conditions. But the habitable zone looks different around different types of stars. Red dwarf stars, the most common stars in the galaxy, are much cooler and dimmer than our Sun. Their habitable zones lie much closer in. A planet might orbit only a few million miles from its star, yet still maintain temperatures suitable for liquid water. This close orbit creates challenges. The planet would likely become tidally locked, with one side permanently facing the star in eternal daylight, while the other freezes in perpetual darkness. Red dwarfs also tend to be more active, producing powerful flares that could strip away planetary atmospheres. Yet despite these challenges, red dwarfs are so numerous and long-lived, some will shine for trillions of years, that they represent countless opportunities for life to emerge. Larger, hotter stars have habitable zones farther out, but these stars burn through their fuel quickly, living only millions or billions of years rather than the tens of billions of years that red dwarfs enjoy. This might not provide enough time for complex life to evolve. On Earth, life emerged relatively quickly, within the first billion years, but complex multicellular life took nearly 3 billion years to appear. Intelligence and technology took even longer. A planet orbiting a massive, short-lived star might develop microbial life, but never progress beyond that before its star exhausts its fuel and dies. The atmosphere plays a crucial role in making a planet habitable. Earth's atmosphere provides pressure that keeps water liquid at the surface. Without atmospheric pressure, water would instantly boil away in the vacuum of space or freeze solid at low temperatures. The atmosphere also provides greenhouse warming. Without it, Earth's average temperature would be well below freezing despite being in the habitable zone. Too little greenhouse effect and a planet freezes. Too much and it becomes an inferno like Venus. The balance must be just right. Planetary mass matters significantly. A planet too small cannot hold onto an atmosphere. Its weak gravity allows atmospheric gases to escape into space. Mars demonstrates this problem. Mars once had a thicker atmosphere and liquid water flowing on its surface, carving the river valleys and lake beds that spacecraft have photographed. But Mars is only about 11% of Earth's mass, and over billions of years, its atmosphere gradually escaped. The loss accelerated because Mars lacks a strong magnetic field to shield the atmosphere from the solar wind, the stream of charged particles from the Sun that can strip away atmospheric gases from unprotected planets. A planet too large faces different problems. If a planet grows massive enough, it begins capturing hydrogen and helium directly from the protoplanetary disk during formation, becoming a gas giant like Jupiter rather than a rocky world with a solid surface. Some theories suggest that planets slightly more massive than Earth, called super-Earths, might actually be better for life than Earth itself. Their stronger gravity could hold thicker atmospheres, providing more greenhouse warming and allowing habitable zones to extend farther from their stars. Their larger size might also mean more volcanic activity, recycling nutrients and maintaining atmospheric composition over longer timescales. Plate tectonics, the process by which Earth's crust is broken into plates that move, collide, and subduct beneath each other, might be essential for long-term habitability. Plate tectonics regulates Earth's climate through the carbon cycle. When carbon dioxide accumulates in the atmosphere, chemical weathering of rocks gradually removes it, and subduction carries carbonate minerals deep into the mantle, where heat releases the carbon dioxide back through volcanic eruptions. This cycle acts as a thermostat, preventing runaway greenhouse or icehouse conditions. Without plate tectonics, a planet might lose this regulatory mechanism, making long-term habitability more difficult. But life is remarkably adaptable, and the conditions necessary for life might be far more flexible than our Earth-based experience suggests. On Earth, extremophiles, organisms that thrive in extreme environments, have shattered assumptions about where life can exist. Bacteria live in boiling hot springs at temperatures exceeding 200 degrees Fahrenheit. Microorganisms thrive in the frigid lakes beneath the Antarctic ice. Life exists in hypersaline lakes many times saltier than the ocean, in acidic pools with pH levels that would dissolve metal, and in alkaline lakes caustic enough to burn skin. These extremophiles prove that life can adapt to conditions that would seem utterly hostile. Deep-sea hydrothermal vents host entire ecosystems based not on sunlight, but on chemical energy. Bacteria oxidize hydrogen sulfide and other chemicals spewing from the vents, and entire food chains build upon these chemosynthetic microbes. This discovery revolutionized thinking about where life could exist. A planet doesn't need sunlight reaching its surface to support life. Chemical energy from geological processes suffices. This realization expanded the search for life to include places like Jupiter's moon Europa and Saturn's moon Enceladus, which have subsurface oceans kept liquid by tidal heating. With no sunlight penetrating miles of surface ice, life might not even require a planet's surface. Europa and Enceladus demonstrate that subsurface oceans beneath ice shells can persist for billions of years. These hidden oceans might contain hydrothermal vents similar to those on Earth's ocean floor, providing chemical energy and raw materials for life. Enceladus actively vents water vapor, organic molecules, and salts into space through cracks in its ice, material that spacecraft have flown through and analyzed. The presence of organic molecules and evidence for hydrothermal activity suggests that Enceladus has at least some of the ingredients necessary for life. Titan, Saturn's largest moon, presents an entirely different possibility. Titan is the only moon in the solar system with a thick atmosphere, and it has lakes and rivers on its surface, but they're filled with liquid methane and ethane rather than water. The surface temperature, at about -300 degrees Fahrenheit, is far too cold for liquid water, but some scientists speculate that life might use liquid methane as a solvent instead of water, with biochemistry based on different chemical reactions more suited to cryogenic temperatures. Such life would be utterly alien, built on completely different principles than Earth's biology, but the basic requirements, a liquid solvent, chemical reactions, energy sources, might still allow life to emerge. The possibility of silicon-based life has long fascinated scientists and science fiction writers. Silicon sits directly below carbon in the periodic table and shares many chemical properties. Both form 4 chemical bonds, allowing them to create complex molecules. But silicon-based molecules are generally less stable and less diverse than carbon-based ones, particularly in the presence of water, which tends to break down silicon compounds. In environments without water, perhaps on a world with liquid hydrocarbons or even molten sulfur, silicon-based biochemistry might be possible, though it would function very differently from life on Earth. Life could potentially use different genetic molecules than DNA and RNA. These molecules store and transmit genetic information using a sugar phosphate backbone with nitrogen-based molecules attached. But chemists have synthesized alternatives called XNAS, xenonucleic acids, that use different sugars or even different backbone structures entirely. These artificial genetic molecules can store information and undergo evolution through selection, suggesting that life elsewhere might have invented entirely different solutions to the problem of heredity. Timescales matter enormously for life's emergence and evolution. On Earth, simple life appeared relatively quickly after conditions became favourable, perhaps within a few 100 million years of Earth's formation. This suggests that the transition from non-living chemistry to living organisms might not require unusual conditions or extraordinary luck. But the transition from simple microbes to complex multicellular organisms took vastly longer, roughly 3 billion years. The development of intelligence and technology required nearly all of Earth's history. A planet might easily develop microbial life, but remain stuck at that level indefinitely if conditions don't favour the evolution of complexity. Some planets might develop life, but lose it. Mars almost certainly had more favourable conditions for life billions of years ago when it was warmer and wetter. If life emerged during that time, it might have gone extinct when Mars lost most of its atmosphere and water, or it might persist in subsurface refuges where liquid water still exists in aquifers deep underground. Venus might have had habitable surface conditions early in its history before the runaway greenhouse effect transformed it into the hellscape it is today. Any life that emerged would have been sterilized, leaving no trace. Rogue planets, worlds ejected from their planetary systems to wander interstellar space, might still harbor life, despite receiving no light from any star. If a rogue planet is massive enough to retain a thick atmosphere, and if it has enough radioactive elements in its interior to provide heat, it could maintain liquid water beneath an ice shell indefinitely. Such planets would be invisible to most detection methods, dark worlds drifting through the galaxy, potentially harboring biospheres in their hidden oceans. Binary star systems, where 2 stars orbit each other, comprise about half of all stellar systems. Planets in these systems could orbit both stars at a large distance, experiencing light from 2 suns, or orbit one star closely while the other remains distant. Either configuration could potentially support habitable planets, though the complex gravitational dynamics make stable orbits more difficult to achieve and maintain over billions of years. The discovery of thousands of exoplanets has revealed that planetary systems come in astonishing variety. Hot Jupiters orbit closer to their stars than Mercury orbits our Sun. Super-Earths, a planet type absent from our solar system, appear to be common. Some systems pack multiple planets into orbits closer than Mercury's. This diversity suggests that habitable worlds might exist in configurations we haven't imagined, orbiting in stable zones within systems that look nothing like our own. Life could exist on other planets through countless permutations of chemistry, energy sources, solvents, temperatures, and planetary conditions. It might be carbon-based like us, or built from silicon or other elements. It might use water or methane or ammonia or substances we haven't considered. It might photosynthesize under a red sun or derive energy from chemical reactions in lightless seas beneath miles of ice. The universe is vast, ancient, and filled with planets and the basic ingredients for life. Elements forged in stars, energy from stellar radiation or geological processes, and the simple passage of time exist everywhere. Whether life has taken advantage of these opportunities elsewhere remains the greatest unanswered question in science, but the conditions that could allow it exist on countless worlds scattered throughout the cosmos. How stars create light and heat. Every star you see in the night sky is a massive nuclear furnace, a sphere of gas so hot and dense at its core that atoms are torn apart and fused back together in reactions that release staggering amounts of energy. The light that reaches your eyes from even the nearest star beyond our sun has travelled for years through the void of space, carrying energy that was created in the unimaginable heat and pressure at that star's core. Understanding how stars create this light and heat means understanding one of the most fundamental processes in the universe, one that has been lighting the cosmos for billions of years and will continue for billions more. Begin at the heart of a star, the core, where conditions are almost beyond comprehension. In our sun, the temperature at the centre reaches about 27 million degrees Fahrenheit. The pressure is equally extreme, about 250 billion times the atmospheric pressure at Earth's surface. Under these conditions, matter behaves in ways completely unlike anything we experience in daily life. The gas is so hot that atoms cannot exist as atoms. Electrons are stripped away from their nuclei, creating a plasma where negatively charged electrons and positively charged nuclei move independently through a churning, seething mass. At these temperatures and pressures, atomic nuclei that would normally repel each other, they're all positively charged, and like charges repel, move so fast that they occasionally collide with enough energy to overcome this electrical repulsion. When hydrogen nuclei, which are simply protons, collide at these tremendous speeds, they can fuse together. This is nuclear fusion, and it's the source of all the energy a star produces. The most common fusion process in stars like our Sun is called the proton-proton chain. Picture two protons colliding at enormous speed in the star's core. Usually, they just bounce off each other, repelled by their mutual positive charge. But occasionally, very rarely, quantum mechanics allows something remarkable to happen. The two protons fuse, and in that instant, one of them transforms into a neutron through a process involving the weak nuclear force. This creates a nucleus of heavy hydrogen, called deuterium, consisting of one proton and one neutron bound together. This single fusion event releases energy in multiple forms. A positron is ejected, the antimatter counterpart of an electron. A neutrino, an almost massless particle that barely interacts with anything, streams away at the speed of light. And energy is released as gamma-ray radiation, the most energetic form of light. The positron almost immediately encounters a regular electron, and they annihilate each other in a burst of energy. The neutrino escapes the star entirely, passing through all the overlying layers as if they weren't there, reaching space in just a few seconds. But this is only the first step. The deuterium nucleus that formed doesn't last long on its own. It quickly collides with another proton and fuses with it, creating a nucleus of helium-3, which has two protons and one neutron. This fusion releases more energy, this time in the form of a gamma ray. Finally, two helium-3 nuclei collide and fuse, forming ordinary helium-4, which has two protons and two neutrons. and releasing 2 protons back into the mix to start the process over again. The net result of all these steps is that 4 hydrogen nuclei have been converted into 1 helium nucleus. And here's the crucial part. The helium nucleus weighs slightly less than the 4 hydrogen nuclei that went into making it. About 0.7% of the mass has disappeared. Where did it go? It was converted into energy, according to Einstein's famous equation, E equals mc squared. That tiny fraction of mass, when multiplied by the speed of light squared, represents an enormous amount of energy. In our Sun, this process converts about 600 million tons of hydrogen into helium every single second. About 4 million tons of matter are completely converted into energy each second. This has been happening for about 4.6 billion years, and the Sun has enough hydrogen fuel to continue for another 5 billion years or so before it exhausts the hydrogen in its core. The energy released in these fusion reactions, created at the core of the star, must somehow make its way to the surface, to be radiated into space as light and heat. This journey is neither quick nor straightforward. The gamma rays produced in the core don't simply stream to the surface. The star's interior is incredibly dense, and a gamma ray photon can't travel far before it collides with an electron or an atomic nucleus. When a high-energy gamma ray photon hits an electron, it typically gets absorbed and then re-emitted, but not necessarily in the same direction, and often at a slightly lower energy. The photon bounces around randomly, absorbed and re-emitted countless times, following what scientists call a random walk. Each interaction changes the photon's direction randomly, so it might move inward toward the core just as often as it moves outward toward the surface. This random walk means that energy takes an extraordinarily long time to travel from the core to the surface. A photon of light can travel from the Sun to Earth, a distance of 93 million miles, in about 8 minutes. But that same photon trying to escape from the Sun's core to its surface, a distance of only about 400,000 miles, takes somewhere between 100,000 and a million years. The exact number is uncertain because the path is so random and complex, involving countless billions of interactions. As the energy works its way outward through this radiative zone, the photons gradually lose energy with each interaction. The high-energy gamma rays from the core become X-rays, then ultraviolet light, then visible light, and eventually include infrared radiation. By the time the energy reaches the outer portions of the star, it has been divided and redistributed among countless photons of various energies. About 2/3 of the way out from the Sun's core, the nature of energy transport changes. The temperature has dropped to the point where atoms can hold onto some of their electrons, and the gas becomes more opaque. In this outer region, called the convection zone, energy is transported primarily by the physical motion of hot gas rather than by radiation. Hot plasma rises toward the surface, cools, and then sinks back down, creating vast circulation cells. Think of a pot of boiling water with bubbles of hot water rising and cooler water sinking, but on a stellar scale where individual convection cells can be larger than Earth. This convection brings hot material from the interior up to the photosphere, the visible surface of the star. Here, finally, energy can escape into space. The photosphere is still incredibly hot by earthly standards, about 10,000 degrees Fahrenheit on the Sun, but it's cool enough that photons can finally stream away into space without being immediately reabsorbed. The light that leaves the photosphere carries information about the star's surface temperature in its colour and spectrum. Hotter stars emit more blue and ultraviolet light, appearing blue or white to our eyes. Cooler stars emit more red and infrared light, appearing orange or red. Our Sun, with a surface temperature around 10,000 degrees, emits most of its energy in the visible part of the spectrum, peaking in the green-yellow range, though it appears white or slightly yellow to our eyes because it emits all colours of visible light. Not all stars use the same fusion process as our Sun. In more massive stars with hotter cores, a different set of reactions called the CNO cycle dominates. This cycle uses carbon, nitrogen, and oxygen nuclei as catalysts to fuse hydrogen into helium. The carbon, nitrogen, and oxygen aren't consumed in the process. They're regenerated at the end of the cycle, but their presence allows the fusion to proceed more rapidly at higher temperatures. Very massive stars can burn through their hydrogen fuel in just a few million years, compared to the Sun's 10 billion year lifetime. The energy output of a star is precisely balanced with its gravity. Gravity tries to compress the star, but the pressure from the hot gas, heated by fusion, pushes outward. These forces are in equilibrium, which is why stars are stable over long periods. If fusion produces too much energy, the star expands and cools slightly, slowing the fusion rate. If fusion slows down, the star contracts and heats up, increasing the fusion rate. This self-regulating mechanism keeps stars stable. The heat generated in a star's core doesn't just produce light, it creates the pressure that holds the star up against its own gravity. Without fusion, a star would collapse under its own weight. This is what happens when a star runs out of fuel. The fusion stops, the pressure drops, and gravity takes over, leading to dramatic events like supernova explosions or the formation of dense stellar remnants. Different layers of the star have vastly different temperatures. The core, where fusion occurs, is the hottest. The temperature decreases as you move outward through the radiative zone and convection zone. The photosphere, the visible surface, is the coolest part of the star proper, though above it lies the chromosphere and corona, regions of the star's atmosphere that are paradoxically hotter than the surface, heated by magnetic fields and shock waves rather than by radiation from below. The amount of energy a star produces is staggering. Our Sun outputs about 386 billion megawatts of power every second. That's more energy than humanity has used in its entire history, released every single second. And the Sun is actually a fairly average, middle-sized star. Some massive stars output 1,000,000 times more energy than the Sun, burning so bright and hot that they exhaust their fuel and die in just a few million years. Every photon of sunlight that warms your face, every ray that allows plants to photosynthesize and create the oxygen you breathe, every bit of light that illuminates the day, began as a fusion reaction in the Sun's core. The energy in that light was created when hydrogen nuclei overcame their electrical repulsion and fused into helium, converting a tiny amount of mass into energy. That energy then spent hundreds of thousands of years bouncing randomly through the Sun's interior before finally reaching the surface and streaming across space to Earth. This process of creating light and heat through nuclear fusion is happening right now in hundreds of billions of stars in our galaxy alone, and in countless more stars throughout the universe. It's been happening since the first stars formed a few 100 million years after the Big Bang, and it will continue for trillions of years into the future, until the last stars finally exhaust their fuel and fade away, leaving the universe dark and cold. But for now, and for the foreseeable future, the universe is filled with light and heat, gifts of the fusion fires burning in the hearts of stars. The biosignatures that reveal living planets. Detecting life on distant planets represents one of the greatest challenges in astronomy. We cannot visit these worlds, cannot scoop up soil samples, cannot peer through microscopes at alien microbes. Most exoplanets appear as nothing more than tiny dips in their star's brightness as they transit, or slight wobbles in the star's position caused by the planet's gravitational pull. Yet from these minimal observations, measurements of light passing through a planet's atmosphere during transit, analysis of the planet's reflected light, characterization of its temperature and size, astronomers hope to determine whether life exists on worlds many light years away. The key lies in biosignatures, detectable signs that life is present, chemical or physical features that cannot easily be explained by non-biological processes, and that point toward the presence of living organisms, modifying their planet's environment in measurable ways. Oxygen stands as the most famous biosignature, the gas that astronomers most eagerly search for in exoplanet atmospheres. On Earth, oxygen makes up 21% of the atmosphere, a concentration vastly higher than would exist without life. Oxygen is highly reactive. It combines readily with rocks, organic molecules, and other materials, removing oxygen from the atmosphere unless something continually replenishes it. On Earth, that something is photosynthetic life. Plants, algae, and photosynthetic bacteria use sunlight to split water molecules, releasing oxygen as a waste product. Without this biological production, Earth's atmospheric oxygen would disappear within a few million years as it reacted with surface materials. Detecting oxygen in an exoplanet's atmosphere would strongly suggest the presence of photosynthetic life, though not definitively. Oxygen can be produced through non-biological processes. Photodissociation of water vapor by ultraviolet light, for instance, can split water molecules and release oxygen. But these abiotic processes typically produce only small amounts of oxygen compared to the abundant oxygen that photosynthesis generates. A planet with significant oxygen in its atmosphere, particularly if that oxygen persists over long periods, would be a compelling candidate for hosting life. However, oxygen alone doesn't guarantee life, and the absence of oxygen doesn't rule out life. Earth's atmosphere contained very little free oxygen for the first 2 billion years or more of life's existence. Early life consisted entirely of anaerobic organisms that didn't produce oxygen. Even after photosynthesis evolved, it took hundreds of millions of years for oxygen to accumulate in the atmosphere, because the gas initially reacted with dissolved iron in the oceans and with rocks before building up in the air. An alien planet might be teeming with life, yet have no oxygen signature if that life hasn't evolved oxygenic photosynthesis, or if oxygen-producing organisms haven't yet generated enough oxygen to overwhelm the chemical sinks that remove it. Methane represents another important biosignature, particularly in combination with oxygen. Methane and oxygen react with each other readily. In the presence of oxygen, methane breaks down relatively quickly through oxidation. For both gases to coexist in significant quantities in an atmosphere, something must be continually producing them faster than they react and disappear. On Earth, biological processes produce both gases. Photosynthesis produces oxygen, while certain bacteria called methanogens produce methane as a metabolic waste product. The simultaneous presence of both gases in substantial concentrations would be difficult to explain through non-biological chemistry alone. Methane itself can be produced abiotically through geological processes. Volcanic activity, hydrothermal systems, and reactions between water and certain rocks can all generate methane without life. But these sources typically produce methane at lower, steadier rates than biological sources. If observations show variable methane levels, perhaps seasonal variations suggesting biological activity that waxes and wanes with seasons, or if methane concentrations are higher than geological sources could explain, this would strengthen the case for biology. Phosphine burst into the biosignature conversation in 2020 when scientists reported detecting this gas in Venus's atmosphere. Phosphine consists of one phosphorus atom bonded to 3 hydrogen atoms, and on Earth it's primarily produced by anaerobic bacteria living in oxygen-free environments. Phosphine is quickly destroyed by ultraviolet light and chemical reactions, so detecting it in an atmosphere suggests something must be continuously producing it. The Venus detection remains controversial. Subsequent observations haven't definitively confirmed the phosphine signal, and some scientists argue that non-biological chemistry could produce phosphine in Venus's harsh environment. But the episode highlighted phosphine as a potential biosignature worth searching for, particularly on worlds very different from Earth. Ozone, a molecule consisting of 3 oxygen atoms, serves as a secondary oxygen biosignature. Ozone forms in atmospheres when ultraviolet light breaks apart molecular oxygen, and the freed oxygen atoms recombine into ozone molecules. Ozone is easier to detect spectroscopically than molecular oxygen, so finding ozone in an exoplanet's atmosphere provides strong evidence that molecular oxygen is also present, which in turn suggests photosynthetic life. Ozone also absorbs harmful ultraviolet radiation, protecting planetary surfaces from DNA-damaging rays. The presence of an ozone layer suggests not only that photosynthetic life produces oxygen, but also that conditions at the surface might be suitable for more complex life that would otherwise be sterilized by ultraviolet radiation. Nitrous oxide, laughing gas, represents another possible biosignature. On Earth, certain bacteria produce nitrous oxide as a byproduct of nitrogen metabolism. Like oxygen and methane, nitrous oxide is reactive and doesn't persist indefinitely in atmospheres without continuous production. Detecting significant amounts of nitrous oxide, particularly in combination with other biosignature gases, would strengthen the case for biological activity. However, nitrous oxide can also be produced abiotically through lightning, volcanic activity, and chemical reactions in the atmosphere, so its detection alone wouldn't be definitive. Sulfur compounds offer additional biosignature possibilities. Dimethyl sulfide, produced by marine phytoplankton on Earth, has a distinctive spectral signature. Hydrogen sulfide, while toxic to most Earth life, is produced by certain bacteria and might be an important gas in alien biospheres based on sulfur chemistry rather than oxygen. Carbonyl sulfide, though produced both biologically and geologically, might still serve as a biosignature when detected in combination with other gases in ways that geological processes can't easily explain. The key to biosignature detection often lies not in finding a single gas, but in detecting combinations of gases that shouldn't coexist in equilibrium. Chemical disequilibrium, the simultaneous presence of gases that react with each other, suggests that something is continually producing those gases, driving the atmosphere away from chemical equilibrium. Life is inherently a disequilibrium phenomenon. Living organisms take in certain chemicals and energy, use them to maintain organization, and grow and excrete different chemicals as waste. This metabolism creates chemical imbalances that wouldn't exist in a sterile abiotic system at equilibrium. Earth's atmosphere is far from chemical equilibrium precisely because life constantly produces gases that react with each other and with the environment. An alien planet with life would similarly maintain chemical disequilibrium, though the specific gases involved might differ completely from Earth. The challenge lies in distinguishing biological disequilibrium from geological or atmospheric processes that can also create unusual gas combinations. Temporal variations in biosignatures provide additional evidence. Seasonal changes in atmospheric composition might reflect biological cycles, plant growth during spring and summer, dormancy during fall and winter. Daily variations might reflect photosynthesis, starting at dawn and stopping at night. Finding these rhythmic patterns would be strong evidence for biology, because non-biological processes rarely produce such regular, predictable cycles tied to light and seasons. Surface features offer another category of biosignatures. On Earth, large-scale biological activity affects the planet's appearance in ways that might be detectable from space. Vegetation reflects light in characteristic ways. The red edge, where plant reflectance increases sharply between red and near-infrared wavelengths, as plants reflect infrared light they cannot use for photosynthesis. This vegetation signature is quite distinctive and might be detectable on exoplanets if vegetation covers substantial portions of the surface. However, alien photosynthetic organisms might not have a red edge. Plants on a planet orbiting a red dwarf star might be black to maximize absorption of the dim red light available, or they might be other colours, entirely depending on their star's spectrum and their photosynthetic pigments. Large-scale colour changes across seasons could indicate biological activity. If part of a planet's surface changes colour seasonally, perhaps from green to brown, as vegetation grows, and then senesces, this would be difficult to explain through geology alone. Detecting such changes would require extremely high-resolution observations across multiple seasons, pushing the limits of even the most advanced telescopes. But future extremely large telescopes might achieve this capability for the nearest exoplanets. Ocean glint patterns might reveal biological activity in oceans. Certain types of marine life produce compounds that affect water's surface tension or create surface films that change how light reflects off the ocean. These effects, though subtle, create characteristic glint patterns that differ from pure water. Detecting such patterns from light years away would be extraordinarily challenging, but might become possible with next-generation direct imaging telescopes. Atmospheric hazes created by biological activity represent another potential signature. On Earth, isoprene and other organic compounds released by plants contribute to atmospheric haze. On Titan, Saturn's moon, photochemistry creates organic hazes that give the atmosphere its orange colour. Distinguishing biological from non-biological hazes would be difficult, but characteristic compositions or variations might provide clues. A planet with organic hazes that change seasonally, for instance, might have biological sources for those hazes. Artificial light on the night side of a planet would be an unambiguous technosignature, a sign not just of life, but of technological civilization. Earth's night side is bright with city lights, electricity use, and various artificial illumination. An alien civilization would likely develop artificial lighting at some stage of technological development, and if they use inefficient lighting that wastes energy by sending light upward into space, rather than directing it all downward toward the ground, their cities might be detectable. However, detecting such faint light from an exoplanet would require extraordinary capabilities beyond current technology, though future direct imaging telescopes might achieve this for the nearest, potentially inhabited worlds. Industrial pollution offers another technological biosignature. Chlorofluorocarbons, CFCs, are entirely artificial. They don't exist naturally and are produced only through industrial chemistry. Detecting CFCs in an exoplanet's atmosphere would be definitive evidence of technological civilization. Other industrial pollutants, nitrogen dioxide from combustion, sulfur dioxide from industry, certain combinations of gases that indicate smelting or chemical manufacturing, might also be detectable. However, some of these gases also have natural sources from volcanoes or other geological processes, so detecting them in amounts far exceeding natural production rates would be necessary to infer industrial activity. The challenge of false positives, non-biological processes that mimic biosignatures, looms large in biosignature detection. Every proposed biosignature has at least some possible abiotic production mechanism. Oxygen can come from water photodissociation. Methane can come from geology. Phosphine might be produced by unknown atmospheric chemistry. Distinguishing true biosignatures from false positives requires careful analysis of gas abundances, combinations, variations over time, and compatibility with the planet's other known properties. Context matters enormously. Finding oxygen in the atmosphere of a planet with a surface temperature of 500 degrees would not suggest life. The planet is too hot for liquid water and likely for any chemistry we would recognize as living. Finding oxygen on a planet in the habitable zone with liquid water on its surface would be far more compelling. Finding oxygen along with methane, nitrous oxide, and seasonal variations in atmospheric composition on such a planet would be extraordinarily difficult to explain without biology. The search for biosignatures requires sophisticated instruments that can analyze light passing through exoplanet atmospheres during transit. As a planet passes in front of its star, some starlight passes through the planet's atmosphere, and gases in that atmosphere absorb light at specific wavelengths, creating an absorption spectrum. By comparing the star's spectrum with and without the planet in front of it, astronomers can determine which wavelengths are absorbed and thus which gases are present in the atmosphere. The James Webb Space Telescope, launched in 2021, has the sensitivity to detect biosignature gases in the atmospheres of certain types of exoplanets, particularly those orbiting small dim red dwarf stars, where the ratio of planet atmosphere to star is more favourable. Future missions propose space telescopes like the Habitable Worlds Observatory or ground-based extremely large telescopes currently under construction will have even greater capabilities, potentially able to characterize Earth-sized planets in the habitable zones of sun-like stars, the most promising targets for finding life as we know it. These missions might detect multiple biosignature gases simultaneously, observe seasonal and diurnal variations, and potentially even directly image planets and analyze their surface properties. The biosignatures that reveal living planets encompass atmospheric gases that shouldn't coexist, chemical disequilibrium maintained by constant biological production, temporal variations that reflect biological cycles, surface properties that change with seasons, and for technological life, pollution, artificial lighting, and deliberate signals broadcast into space. Each signature provides a puzzle piece, and no single piece definitively proves life. But multiple signatures detected together, in combinations difficult to explain through non-biological processes, could provide compelling evidence that we've detected life beyond Earth, transforming the ancient question of whether we're alone from philosophy into science, revealing that the universe contains not just planets and stars, but living worlds where chemistry has crossed the threshold into biology, where organisms grow and reproduce and evolve, where perhaps intelligence has emerged to contemplate its own existence and wonder, as we do, whether anyone else is out there among the countless worlds orbiting distant stars. The incredible density of neutron stars. Imagine taking the entire mass of our Sun, a sphere so large that over 1 million Earths could fit inside it, and compressing it down to the size of a city. Not a large metropolitan area, sprawling across thousands of square miles, but just the central core, perhaps 12 or 15 miles across. This is a neutron star, an object so dense that a single teaspoonful of its material would weigh about 1 billion tons on Earth. To put that in perspective, that single teaspoon would weigh more than all the cars, trucks and buildings in a major city combined. This density is so extreme that it represents a fundamentally different state of matter, one that can only exist under the most extraordinary conditions in the universe. Neutron stars are born in the violent death throes of massive stars. When a star much larger than our Sun, typically at least 8 times more massive, exhausts the nuclear fuel in its core, it can no longer generate the heat and pressure needed to support itself against its own gravity. The core collapses catastrophically in less than a second, falling inward at speeds approaching 1/4 of the speed of light. The outer layers of the star, rebounding from this collapse, are blown away in a supernova explosion that briefly outshines an entire galaxy. What remains at the centre, crushed under its own gravity to densities that boggle the mind, is a neutron star. To understand how neutron stars achieve such incredible density, you need to understand what happens to matter under extreme compression. In normal matter, atoms are mostly empty space. The nucleus of an atom containing protons and neutrons occupies only a tiny fraction of the atom's volume. The rest is empty space with a few electrons orbiting at relatively vast distances. In a solid object, like a piece of iron or a rock, the atoms are packed as closely together as the electromagnetic forces between them allow, but there's still enormous amounts of empty space within each atom. As you compress matter to higher and higher densities, you eventually overcome the forces that keep atoms intact. The electrons are stripped away from their nuclei, creating a plasma of free electrons and atomic nuclei. Compress further, and the electrons themselves are forced to occupy higher and higher energy states due to quantum mechanical principles. Eventually, at densities found in white dwarf stars, electron degeneracy pressure provides the support against gravity. The electrons can't be compressed any further without violating the Pauli exclusion principle, which forbids identical particles from occupying the same quantum state. But if you compress matter beyond even this point, as happens in the core collapse of a massive star, something remarkable occurs. The electrons are forced so close to the protons in atomic nuclei that they combine through a process called electron capture. A proton and an electron merge to form a neutron, releasing a neutrino in the process. This happens not just occasionally, but to nearly every proton in the collapsing core. Within a fraction of a second, the matter that was once composed of atoms, with protons, neutrons, and electrons maintaining their separate identities, transforms into a sea of neutrons, packed together so tightly that they're essentially touching. The neutrons themselves now provide the pressure that supports the star against further collapse. Just like electrons, neutrons obey the Pauli exclusion principle and cannot be compressed indefinitely. This neutron degeneracy pressure halts the collapse, but only after the matter has been compressed to densities comparable to that of an atomic nucleus. In fact, you can think of a neutron star as essentially a single gigantic atomic nucleus, several kilometers across, containing more neutrons than there are atoms in all the planets of our solar system combined. The density at the center of a neutron star is estimated to be around 500 million to perhaps a billion tons per cubic centimeter. At these densities, a cubic centimeter, about the size of a sugar cube, would contain more mass than Mount Everest. The entire mass of humanity, every person on Earth, could be compressed into a volume smaller than a grain of sand at neutron star densities. These numbers are so far beyond everyday experience that they almost lose meaning, but they represent real physical conditions that exist in these objects. The structure of a neutron star is complex and layered. At the surface, there's a thin atmosphere only a few centimeters thick, composed of hydrogen, helium, or heavier elements, depending on the star's history. Below this lies the outer crust, where matter exists in a crystalline lattice. Here, atomic nuclei, now incredibly neutron-rich and unlike any nuclei found on Earth, are arranged in a solid structure with a sea of electrons moving between them. This crust is extraordinarily rigid. It's been calculated that the material of a neutron star's crust is about 10 billion times stronger than steel. Deeper into the neutron star, at densities about 1 million times that of normal atomic nuclei, the inner crust begins. Here, neutrons start to leak out of the nuclei and form a superfluid that exists between and around the nuclei. A superfluid is a state of matter with zero viscosity. It flows without any resistance whatsoever. This neutron superfluid can exhibit bizarre quantum mechanical behavior on a macroscopic scale. Below the crust lies the outer core, where the density becomes so high that nuclei dissolve entirely into a uniform liquid of neutrons, with a small admixture of protons and electrons to maintain charge neutrality. The neutrons in this region form a superfluid, while the protons form a superconductor, a state where electrical current can flow without resistance. These quantum fluids make up the bulk of the neutron star's interior. At the very center, in the inner core, conditions become so extreme that we're not entirely certain what happens. The density may exceed that of atomic nuclei by a factor of several times. At these densities, neutrons themselves might break down into their constituent quarks, creating what's called a quark-gluon plasma, or strange quark matter. Alternatively, other exotic particles predicted by physics but never observed might appear. The center of a neutron star is one of the few places in the universe where matter exists in states that can't be recreated or studied in laboratories on Earth. The incredible density of neutron stars creates gravitational fields so strong that they noticeably warp space-time. At the surface of a neutron star, gravity is about 200 billion times stronger than on Earth. If you could somehow stand on a neutron star's surface, though you would instantly be crushed and vaporized, you would weigh 200 billion times more than you do on Earth. A fall from even a tiny height of 1 centimeter would be fatal, as you would hit the surface at a significant fraction of the speed of light. This intense gravity affects light itself. Photons climbing out of a neutron star's gravitational well lose energy through gravitational redshift. Light that starts as high-energy X-rays at the surface might emerge as lower-energy radiation by the time it escapes into space. The gravity also bends light rays, causing light from the far side of the neutron star to curve around and become visible to an observer. This means you could potentially see more than half of the neutron star's surface at once, as light from behind the star bends around it to reach your eyes. The intense gravity also means that space and time are severely warped near a neutron star. Clocks at the surface of a neutron star run about 30% slower than clocks far away in flat space-time. This time dilation is a real physical effect. Processes genuinely occur more slowly in the strong gravitational field at the surface compared to regions far from the star. The rotation of neutron stars adds another layer of extremes to their already extreme nature. Many neutron stars spin rapidly, some completing hundreds of rotations per second. This happens because of conservation of angular momentum. When the core of the parent star collapses, any rotation it had is amplified enormously as the radius shrinks. Just as a figure skater spins faster when pulling their arms in, a collapsing stellar core spins faster as it shrinks. The result can be a neutron star spinning so fast that its equator is moving at a significant fraction of the speed of light. The fastest spinning neutron star known rotates 716 times per second. Imagine an object with more mass than the Sun, compressed to the size of a city, spinning around more than 700 times every second. The surface at the equator of this neutron star is moving at about 24% of the speed of light. At these rotation rates, centrifugal forces become significant, causing the neutron star to bulge at the equator and flatten at the poles. Yet even with this rapid rotation and the outward force it creates, the neutron star holds together, a testament to the incredible strength of neutron-degenerate matter and the overwhelming power of its gravity. The magnetic fields of neutron stars are among the strongest in the universe. The collapse that forms a neutron star compresses and amplifies any magnetic field present in the parent star's core. The result can be magnetic fields 1 trillion times stronger than Earth's magnetic field. Some neutron stars, called magnetars, have fields even stronger, up to 1,000 times more intense still. At these field strengths, quantum mechanical effects become important. The vacuum of space itself becomes polarized by the magnetic field, affecting how light propagates. Atoms stretched by these fields become elongated, many times longer than they are wide, fundamentally changing their properties. These magnetic fields, combined with rapid rotation, power some of the most energetic phenomena in the universe. Charged particles, accelerated along magnetic field lines, emit beams of radiation from the magnetic poles. If these beams sweep across Earth as the neutron star rotates, we detect regular pulses of radiation, which is why many neutron stars are called pulsars. The precision of these pulses rivals that of atomic clocks, with some pulsars maintaining their timing to within microseconds over years or decades. The density of neutron stars also means that they have very deep gravitational wells. The escape velocity from the surface of a typical neutron star is about 150,000 kilometers per second, roughly half the speed of light. This means that matter falling onto a neutron star from a companion star in a binary system releases tremendous amounts of energy. The infalling material accelerates to these extreme velocities and slams into the surface with incredible force, heating to temperatures of hundreds of millions of degrees and emitting intense X-rays and gamma rays. Neutron stars can also collide with each other in binary systems where two neutron stars spiral together due to the emission of gravitational waves. When they finally merge, the collision creates conditions even more extreme than those in individual neutron stars. The merger produces a burst of gravitational waves that ripple through space-time, along with electromagnetic radiation across the spectrum. These collisions are thought to be the primary source of heavy elements like gold and platinum in the universe, forged in the incredibly dense, hot material ejected during the merger. The study of neutron stars provides a unique laboratory for physics under extreme conditions. The densities, magnetic fields, rotation rates, and gravitational fields found in and around neutron stars simply don't exist anywhere else that we can observe. By studying these objects, physicists can test theories about how matter behaves at nuclear densities, how gravity warps spacetime in strong field regimes, and how quantum mechanics manifests on macroscopic scales. Every observation of a neutron star, every measurement of its mass, radius, rotation, or cooling rate provides constraints on fundamental physics that cannot be obtained any other way, offering glimpses into realms of matter and energy that push the very boundaries of our understanding. The crystal-like structures in space, deep within the cosmos, far from the warmth of any star, materials arrange themselves into patterns that would look familiar under a microscope on Earth. These crystalline structures form in the most unexpected places, defying the assumption that space is simply a chaotic void of random particles and radiation. In the cold depths between stars, water molecules slowly drift together, each one eventually finding its place in an organized lattice. The process happens atom by atom, molecule by molecule, as temperatures hover just a few degrees above absolute zero. Unlike the rapid freezing we experience on Earth, these ice crystals have time, millions of years sometimes, to achieve near-perfect geometric arrangements. The hexagonal patterns repeat endlessly, creating structures that catch and reflect starlight in particular ways that astronomers can detect from across the galaxy. Silicate minerals also crystallize in space, forming within the cooling outflows of dying stars. As a red giant sheds its outer layers, temperatures drop from thousands of degrees to just hundreds, creating conditions where molten rock can slowly solidify into crystals. These aren't the rough, irregular chunks we might expect. They're often perfectly formed olivine crystals, the same green mineral found in beach sand on Earth, but floating freely in the vacuum between worlds. Some of these crystals are microscopic, barely larger than the wavelength of light, while others grow to sizes that would be visible to the naked eye if you could somehow hold one. The environment around young stars presents another laboratory for crystal formation. In the swirling disk of gas and dust that will eventually become planets, temperatures vary dramatically with distance from the central star. There's a boundary, a line in space, where water transitions from gas to solid ice. Scientists call this the snow line or ice line, and it's here that water crystallizes directly from vapor without ever being liquid. The crystals that form are often elaborate, with branching structures that would rival any snowflake on Earth. These become the building blocks of comets and the icy cores of giant planets. Carbon takes on crystalline forms in space as well. In the hearts of ancient stars where pressures and temperatures reach extremes, carbon atoms arrange themselves into diamond structures. These aren't the large gemstones of jewelry stores, but microscopic grains that get expelled into space when the star dies. Scientists have found these pre-solar diamonds in meteorites that have fallen to Earth, tiny time capsules that formed before our solar system even existed. Each one contains isotope ratios that don't match anything that formed near our sun, proving they crystallized around entirely different stars. The surfaces of comets hide their own crystalline secrets. When these icy bodies spend long periods in the cold outer reaches of the solar system, the water ice in them gradually transitions from an amorphous glass-like state into a crystalline form. This transition releases trapped gases, sometimes causing the comet to briefly become more active, even when it's far from the sun. The crystalline ice has a different density than the amorphous ice, creating stresses within the comet's structure that can cause chunks to break away. Methane ice crystallizes on the surfaces of distant worlds, like Pluto and Neptune's moon Triton. At the frigid temperatures found in the outer solar system, methane behaves much like water ice does on Earth. It forms mountains and plains, fills craters, and even creates frost that glitters on the surface. The crystal structure of methane ice determines how it flows and breaks, shaping these distant landscapes in ways that mirror glacial processes on Earth, but with a completely different material. Salt crystals have been detected in the geysers of Saturn's moon Enceladus. Deep beneath this tiny world's icy crust lies an ocean of liquid water, kept warm by tidal heating from Saturn's gravity. When water from this ocean erupts through cracks in the ice, it immediately begins to freeze in the vacuum of space. But before it freezes completely, dissolved salts precipitate out, forming tiny crystalline particles that get ejected into space along with the ice. These salt crystals tell scientists about the chemistry of that hidden ocean. In the dusty clouds where stars form, silicate grains develop crystalline structures that affect how they interact with light and heat. When these grains are hit by shock waves from nearby stellar explosions, the intense but brief heating can transform their atomic structure, creating crystals with specific properties. The type of crystal that forms depends on the exact composition of the grain and the intensity of the heating event. Some become forsterite, a magnesium-rich crystal that glows warmly in infrared light. Others become enstatite, a pyroxene mineral with a different crystal lattice. The process of crystallization in space isn't always slow and gradual. Sometimes it happens in moments. When two white dwarf stars collide, the tremendous pressures and temperatures can cause carbon to crystallize almost instantaneously into diamond. The resulting object might have a core of crystallized carbon surrounded by layers of other materials, a cosmic gemstone larger than our Earth itself, hidden from view by its outer envelope. Amino acids, the building blocks of proteins, have been found in meteorites in crystalline forms. These organic crystals formed in the cold of space, where complex molecules could arrange themselves into ordered structures. The handedness of these crystals, whether they twist to the left or right, has implications for how life might have begun on Earth. The predominance of certain crystal orientations in space-formed amino acids might explain why life on Earth uses left-handed amino acids almost exclusively. Iron and nickel alloys crystallize in the cores of asteroids, forming structures called Widmanstätten patterns. These form when molten metal cools extraordinarily slowly over millions of years, allowing different crystal phases to separate and create geometric patterns. When metallic meteorites are cut, polished, and etched with acid, these patterns become visible as interlocking crystals that look almost like abstract art. The size and arrangement of these crystals tell scientists about the thermal history of the asteroid they came from. Sulfur compounds crystallize on the surface of Jupiter's moon, Io, the most volcanically active body in the solar system. The sulfur takes on different crystalline forms depending on temperature, creating a multicolored landscape of yellows, reds, oranges, and whites. Each colour represents a different allotrope of sulfur, a different way the atoms can arrange themselves into crystal structures. These crystals don't last long in their original form. The intense radiation from Jupiter and the constant volcanic resurfacing mean that sulfur crystals are continually forming, breaking down, and reforming. In the coldest clouds of interstellar space, carbon dioxide freezes into dry ice crystals. These crystals coat the surfaces of dust grains, creating icy mantles that change how the grains interact with each other and with radiation. The crystal structure of this frozen carbon dioxide determines how easily it can trap other molecules, creating complex ices that contain dozens of different compounds, all organized in crystalline matrices. Phosphates and other minerals crystallize in meteorites under conditions that never occur on Earth today. These crystals preserve information about the early solar system, including the presence of water and the temperatures that existed on their parent asteroids. Some contain tiny pockets of liquid water trapped within the crystal structure, water that has been sealed away for over 4 billion years. The magnetic minerals in meteorites show evidence of crystallization in the presence of magnetic fields. The way iron oxide crystals align as they form reveals information about magnetic fields that existed around the young sun and in the interiors of molten asteroids. These crystals act as fossil compasses, recording ancient magnetic environments that have long since disappeared. Quartz crystals, so common on Earth, form in space as well, though through different processes. In the shocked material around impact sites, the intense pressure can cause silicon and oxygen to crystallize into quartz with unusual properties. Some of these crystals contain defects and inclusions that could never form under Earth's surface conditions, making them distinct markers of extraterrestrial origin. The study of crystalline structures in space reveals that the same fundamental physics that governs crystal formation in earthly laboratories operates throughout the universe. Temperature, pressure, chemical composition, and time determine what forms, but the basic rules remain constant whether the crystals form in a laboratory, deep in the Earth, or in the cold expanse between stars, where matter continues to organize itself into patterns of surprising complexity and beauty. The solar wind that flows through space. From the surface of the sun, an invisible river flows outward in all directions, streaming past the planets and extending far beyond the orbit of Pluto into the distant reaches of the solar system. This is the solar wind, a continuous flow of charged particles, primarily electrons and protons, that escape from the sun's outer atmosphere and race through space at speeds ranging from 250 to over 500 miles per second. This wind carries with it pieces of the sun itself, along with magnetic fields that thread through the solar system, creating an enormous bubble of solar influence that shapes the space environment around every planet. The story of the solar wind begins in the sun's corona, the outermost layer of the solar atmosphere that extends millions of miles above the visible surface. The corona is paradoxically much hotter than the surface below it, while the sun's visible surface, the photosphere, has a temperature of about 10,000 degrees Fahrenheit. The corona reaches temperatures exceeding 2 million degrees. This extreme heating, still not completely understood, but likely involving magnetic fields and wave energy, gives particles in the corona so much energy that many of them move faster than the sun's escape velocity. Imagine standing at the sun's surface and throwing a baseball upward. To escape the sun's gravity, you would need to throw it at about 380 miles per second. In the corona, thermal energy heats particles to such extreme temperatures that a significant fraction of them are moving faster than this escape velocity. These particles don't fall back to the sun, they stream away into space, carrying energy and momentum with them. The sun is essentially evaporating, losing mass continuously through this process, though at a rate so slow that it would take trillions of years to evaporate completely. The solar wind is not uniform. It flows faster from some regions of the sun than others, creating a complex structure as it expands outward. Above the sun's equatorial regions, where magnetic field lines tend to loop back to the surface, the solar wind emerges more slowly, typically around 250 miles per second. But at the sun's poles and in coronal holes, regions where magnetic field lines extend far into space, rather than looping back, the wind flows much faster, reaching speeds of 500 miles per second or more. These variations in speed create interaction regions where fast solar wind catches up to slow solar wind. Imagine cars on a highway where fast-moving traffic overtakes slower-moving traffic. The fast solar wind compresses the slow solar wind ahead of it, creating regions of enhanced density and magnetic field strength. These co-rotating interaction regions, named because they rotate with the sun as it spins, sweep through the solar system like a spiral pattern, buffeting planets with alternating streams of slow and fast wind. As the solar wind flows outward, it carries the sun's magnetic field with it. The magnetic field lines become stretched and twisted, creating a spiral pattern much like water from a rotating garden sprinkler. This interplanetary magnetic field threads through the entire solar system, connecting magnetically active regions on the sun to the distant reaches of space. When magnetic field lines from different regions of the sun come together, in space they can reconnect, releasing energy and accelerating particles to even higher speeds. The solar wind is not just a steady breeze but includes violent gusts and storms. When an eruption occurs on the sun, a solar flare or a coronal mass ejection, enormous quantities of plasma and magnetic field can be hurled into space far faster than the normal solar wind. A coronal mass ejection can contain billions of tons of material moving at speeds up to several thousand miles per second. When one of these structures reaches Earth, typically 1 to 3 days after leaving the sun, it can compress Earth's magnetic field, trigger spectacular auroras, and potentially disrupt satellites, power grids, and communication systems. The journey of a solar wind particle from the sun to Earth takes about 4 to 5 days travelling at typical speeds. During this journey, the particle encounters very little. Space between the sun and Earth is remarkably empty. A cubic inch of the solar wind near Earth contains only about 5 to 10 protons, far more tenuous than even the best vacuum we can create in laboratories on Earth. Yet despite this extreme sparseness, the solar wind carries significant momentum and energy simply because of the vast volume through which it flows and the speeds at which it travels. When the solar wind encounters a planet, what happens depends on whether that planet has a magnetic field. Earth's magnetic field creates a protective bubble called the magnetosphere that deflects most of the solar wind around the planet. The interaction is dynamic and complex. The leading edge of Earth's magnetosphere, called the bow shock, is where the supersonic solar wind first encounters Earth's magnetic field and slows down abruptly, much like air piling up in front of a supersonic aircraft creates a shock wave. This shock heats the solar wind and diverts it around Earth's magnetosphere, creating a turbulent boundary layer called the magnetosheath. Some solar wind particles do manage to penetrate into Earth's magnetosphere, particularly when reconnection occurs between the interplanetary magnetic field and Earth's magnetic field. These particles get funneled along Earth's magnetic field lines toward the polar regions, where they collide with atoms in the upper atmosphere, creating the shimmering curtains of light we call auroras. The green and red colours come from oxygen atoms at different altitudes being excited by these collisions, while nitrogen produces blue and purple hues. Planets without magnetic fields like Mars and Venus experience the solar wind very differently. Without a protective magnetic bubble, the solar wind interacts directly with the upper atmosphere. Over millions of years, this interaction strips away atmospheric particles, carrying them off into space. Mars, which once had a thicker atmosphere and possibly liquid water on its surface, has lost much of its atmosphere to this process. The solar wind literally peels away the outer layers of the Martian atmosphere, particularly during strong solar storms, gradually transforming Mars from a potentially habitable world to the thin, dry atmosphere we observe today. The Moon, with neither atmosphere nor magnetic field, receives the full force of the solar wind directly on its surface. Solar wind particles impact the lunar regolith, becoming implanted in the soil. Over billions of years, this process has altered the chemistry and appearance of the lunar surface, darkening it and creating what scientists call space weathering. Ancient lunar rocks brought back by Apollo astronauts contain trapped solar wind particles that serve as a record of how the Sun's output has changed over time. Giant planets like Jupiter and Saturn have enormous magnetospheres that extend millions of miles into space. Jupiter's magnetosphere is so large that if we could see it from Earth, it would appear several times larger than the full moon in the sky. The solar wind compresses these magnetospheres on the side facing the Sun and stretches them into long tails on the night side. Within these giant magnetospheres, the interaction between the solar wind, the planet's magnetic field, and particles from the planet's moons creates some of the most intense radiation environments in the solar system. The solar wind doesn't flow forever. Far from the Sun, billions of miles beyond the orbits of the planets, it begins to slow down as it encounters the interstellar medium, the dilute gas and plasma that fills the space between stars. The Voyager spacecraft, launched in 1977, have travelled far enough to cross the boundary where the solar wind slows to subsonic speeds, called the termination shock. This boundary is not spherical, but is pushed outward in the direction the solar system is moving through the galaxy and compressed in the opposite direction. Beyond the termination shock lies a region called the heliosheath, where the solar wind has slowed but still moves outward, compressed and heated by its interaction with the interstellar medium. The exact shape and extent of this region depend on the strength of the solar wind and the pressure of the interstellar medium outside. Voyager 1 and Voyager 2 have now crossed even farther, passing through the heliopause, the outer boundary where the solar wind effectively stops and interstellar space begins. They are now in a region where the dominant flow is no longer from the Sun, but from the galaxy itself. The structure created by the solar wind, this vast bubble of solar influence, extending billions of miles in all directions, is called the heliosphere. It serves as a partial shield, deflecting some of the cosmic rays that stream through the galaxy. Without this protection, the flux of high-energy particles reaching the inner solar system would be higher, potentially affecting planetary atmospheres and creating more radiation hazards for any life on planetary surfaces. The solar wind varies with the Sun's activity cycle. During solar maximum, when the Sun is most active with many sunspots and frequent eruptions, the solar wind is stronger, more variable, and more likely to include fast-moving coronal mass ejections. During solar minimum, when the Sun is quieter, the wind becomes more regular, though still continuous. This 11-year cycle affects space weather throughout the solar system, influencing everything from auroral activity on Earth to the radiation environment encountered by spacecraft. The composition of the solar wind provides a sample of the Sun's outer layers. While predominantly hydrogen, both protons and electrons, the wind also contains helium, making up about 4% of the particles, along with trace amounts of heavier elements, like carbon, nitrogen, oxygen, neon, magnesium, silicon, and iron. These heavier elements are present in much smaller quantities but provide valuable information about solar composition and the processes occurring in the corona. Different types of solar wind have different characteristics. The slow solar wind is denser and cooler, while the fast wind is more tenuous but carries more kinetic energy due to its higher speed. Transient events like coronal mass ejections create temporary structures in the solar wind with dramatically enhanced density, speed, and magnetic field strength. These variations create a constantly changing space environment that spacecraft and planets must navigate. The solar wind also carries information outward from the Sun. Disturbances created by solar activity propagate through the solar wind, and by observing how these disturbances evolve and interact as they move through space, scientists can learn about the properties of the wind itself and the magnetic fields threading through it. Spacecraft throughout the solar system serve as sentinels, measuring the solar wind's properties at different locations and providing a three-dimensional view of how this invisible river flows through our cosmic neighborhood. Every star produces a stellar wind, analogous to our solar wind, and these winds play important roles in stellar evolution and in shaping the environments around other planetary systems. Hot, massive stars produce fierce stellar winds that can carry away significant fractions of the star's mass over its lifetime. Cool, evolved stars like red giants produce slower but denser winds. Understanding our own solar wind provides insights into these stellar winds throughout the galaxy, connecting the processes occurring in our immediate space environment to the broader evolution of stars and planetary systems across the universe.